This is a lesson on energy and phase change. Up until now, what we've been talking about is when you add energy, the temperature increases. If the temperature increases, that means the particles are moving faster. So if you add energy, you heat something up, it goes to increase the kinetic energy or the motion of the particles, which means the temperature goes up. Today we're going to talk about phase changes, where the energy is going in to increase the potential energy. And in this case, we're talking about if you're adding energy, breaking some of the IMF, intermolecular forces, or the bonds between the molecules. If you add energy, you break IMF. If you remove energy, it forms IMF, or bonds between solids and liquids. If the amount of energy needed to boil is much greater than the energy needed to melt, melting breaks some of the bonds. Boiling requires you to break all of the bonds. So there's more energy needed to boil something than there is to melt something, because you're only breaking some of the bonds. The energy needed to melt or boil, melting and boiling, the heat of fusion, HF, heat of fusion, is the energy needed to change 1 gram of substance. It's the amount of energy you need to add to melt 1 gram, or not melt and boil, it's melt and freeze. You need to put in that amount of energy to melt 1 gram of substance, or it's the amount of energy you need to remove to freeze 1 gram of substance. You cannot use MC delta T because the change in temperature is 0. When you start to melt something, it's ice, say ice, at 0 degrees Celsius. When you get done melting the ice cube, you have ice water at 0 degrees Celsius. So that means that change in temperature would be 0, which means it does not take any energy to melt ice, which we know is not true. So what we have is the equation, the new equation for phase change, delta H is equal to M H sub F. Mass is in grams. H sub F is something per gram, energy per gram, and this is delta H. If this is calorie per gram, you're going to end up with calories because the grams will cancel. If it's kcals, kcals. If it's joules, you get joules. So if you're asked for how much energy or how many kcals or how many joules of energy is needed, you're going to multiply the two numbers together. For example, you have 100 grams of a substance with a specific heat capacity of 2.5 joules per gram. If you multiply these two together, the grams cancel, and you get 250 grams of energy, 250 joules of energy are needed. You either need to add that much to melt, or you need to remove that much energy to freeze that substance. If you could have a question where you're asking for how much mass or what is the specific heat capacity of a substance. In that case, you have something like you have 10,000 calories are needed to melt so many grams of a substance with a specific heat content of 50. You divide both sides by 50, and you get 1,000 divided by 5, 200 grams. So you can melt 200 grams of that substance. The next thing is boiling, condensing, and this is H sub V, which is heat of vaporization. And that's the energy needed to change 1 gram of substance. It's the energy needed to boil, the energy needed to put in to boil, or it's the energy you get out if you condense. The math examples are exactly the same up above, except instead of HF, you have HV. So the previous examples would work for the same thing. The last thing we're going to do is phase change, or cooling curve, or heating curves. You'll have to draw and label on a quiz or a test. For example, of a heating curve, here you have your temperature. This axis you have your time. If it's a heating curve, you're going to start low temperature, so you're going to be down here. This is your starting temperature. And if you have a solid at a low temperature, first thing you're going to do is have to add energy to it. You're going to continuously add energy with time, and your temperature is going to increase because the particles are moving faster and faster and faster until you hit this point, which is the melting point. At the melting point, the temperature does not change, so it levels off until the last bit of the solid has melted away. Then you can do and now you got water, or liquid, so it can increase until it hits the boiling point. Then it gets leveled off again until it's all evaporated, and then you can shoot up some more. So right here is your ending point, ending temperature. The slope of the lines tells you the specific heat capacity. The sharper the line, the smaller the specific heat capacity. The length of the horizontal segments tells you how big the HF or HV is. This is how you draw the heating curve, and then what's left is labeling it. This down here at the bottom diagonal is always a solid. The middle diagonal is always the liquid, and the upper diagonal is always the gas. Solid to liquid, what's going on here? You're melting. liquid to gas, what's going on here? You're boiling. And that's the heating curve. The other thing that you got to do is a cooling curve. The cooling curve is kind of backwards. Time, temperature, cooling curve. Except now you're going to start at a high temperature, and you'll always have a diagonal to start with. But instead of going up, you're going down because it's decreasing temperature. So it goes down, flattens out, goes down again, flattens out, and down again. The upper diagonal is always gas, the middle is always liquid, the ending one is always solid. Between liquid and solid is freezing. And between gas and liquid is condensing. The only other thing that you got left to do is, for extra credit, it's not required, how much energy does it take to go from a solid at the starting temperature to a gas at the ending temperature? Now, there's not one equation because there's 5 different segments. So you got to do mc delta T for the solid, mhf for melting, mc delta T for boiling, but this is going to be a different C and change temperature, delta T. Boiling is mhv, and a gas is mc delta T again. Again, C and delta T will be different numbers. The mass will be consistent throughout the whole deal because you're heating and cooling the same mass. So if you're going all the way from a solid to a gas heated up beyond its boiling point, you're going to have 5 line segments. So you're going to have to do the 5 numbers and add them up. It's not too difficult, it's just a lot of work and details. Can't miss anything. That ends this lesson on energy and phase change.